Dr. Deepak Bose, Senior Scientist in the Entry Systems and Technology Division.
Thank you, Maria. Thank you, everyone. Once my slides are up, we'll get started. So I'll be mostly talking about the entry, descent, and landing. Essentially, what has been called the riskiest move in the whole planetary mission is to take this 3-ton entry vehicle and land them safely on the ground. So, and this is the most ambitious mission we have ever undertaken. And if you go back in history, landing on Mars has not been easy. Of all the missions that we have sent as humans, about half of them have been successful. And this is by far the most capable mission, and this is showing some resounding success. So this is the entry vehicle, which is 4.5 meter diameter with a heat shield in front, made of a material called pica, as Tom Edwards said. This is invented here at NASA Ames. It was tested here in our ArcJet facilities, less than a mile from here, and it was sized and designed. The architecture was developed at this center. So before I get into how did this heat shield perform, and we embedded this heat shield with a lot of sensors, so we know exactly what it did, as whatever our sensors could read. So before we get into that, let me give you a brief overview of the entry, descent, and landing process of this unprecedented acrobatics that goes on for 7 minutes, and everything must go right, and there are a lot of potential of things going wrong. So it all starts at about 150 kilometers above the surface of Mars. When the vehicle begins to sense the atmosphere. It moves at around 13,000 miles per hour, extremely high speed. And as it senses the atmosphere, it just feels like braking. It just wants to brake. There's so much drag because of the atmosphere. It goes from 13,000 miles per hour to 400 miles per hour in about 4.5 minutes. So there's a lot of braking, a lot of heating, a lot of friction and rubbing. Where does all that energy go? I'll talk about that a little bit. What makes this mission more challenging is this is the largest entry vehicle we have ever flown. And this is, a car can fit inside this. It looks small from up there, but a car can fit inside this. But it's also the heaviest entry vehicle. When it entered, it weighed about 3,200 kilogram, which is about 3-ish tons. It had the new heat shield material called pica, which won the NASA Invention of the Year back in 2007, invented right here, as I mentioned. And the reason we had to go to this new heat shield material is because the entry was so severe compared to the last entries that we have seen. We had to abandon the heritage material that had been in use in past 36 years and had to go to this new material, which of course performed very well, as I'll show you later. So while this is braking and going through this immense amount of heating, this is also flying like an airplane. This is not just falling to the ground like past missions. This is flying. It's guiding itself to the target. It has a lift, kind of like an airplane, and it's directing that to guide to its target. That's what gives us the precision landing, and that's where the scientists want to go to a specific point on Mars. And this technology is key to taking us to the point where we want to go. Once it has dissipated most of its energy, around 400 miles per hour, the parachute is triggered, and this again is the largest parachute we have ever flown. It is deployed at Mach 2 supersonic parachute, and for a large parachute like this, we need a large wind tunnel, and that's what Robbie will be talking about after me, which is also what we have here at NASA Ames. Once it goes down to subsonic speeds, the heat shield separates, the pica heat shield separates so that we can actually see the ground. Up until that point, there is no sight, there's no measure of where the ground is, except you start integrating from the initial point. At this point, you start to collect data on where you are and how far away from the surface you are, and then the descent stage separates from the parachute action system. And this is what is called the sky train maneuver. As the descent stage reaches closer to the ground, it doesn't touch the ground, but lowers the tether that carries the rover to the ground. And when it senses that it's reached the ground, it cuts the tether and flies away. And that's the sky train maneuver last year. This is something that was never been tried before, and this was key to really landing this heavy piece of equipment, 900 kilogram of equipment on the surface of Mars. So that's what makes it unique. This is not something that has been done in the past, and this is something that really demonstrates a lot of technologies that we would need to land humans one day on Mars. So let's talk a little bit about entry, which is closer to what we do here. So the spacecraft entered Martian atmosphere 13,000 miles per hour. That's a lot of energy, and it's heading toward Mars, heading toward ground at that speed. That energy is equal to about 20 freight trains running at 75 miles an hour. You got to stop this. And where does all that energy go? That's megawatt hours of energy, and that goes, 99% of that energy is dissipated during the first 4.5 minutes before the parachute deployment. And that energy goes into ripping apart the molecules of the atmosphere of Mars. The carbon dioxide molecules get ripped apart into atoms. A plasma is formed about 10,000 degrees around the spacecraft. And the Pico heat shield that we developed here is all that stands between the plasma and the payload during that 4.5 minutes. And this is a significant amount of test and analysis and simulation on the largest supercomputer go into really designing this heat shield. And this is an image of a test that's being conducted, that's been conducted here at NASA Ames. So we had sensors on this vehicle, and we actually, for the first time, were able to see what happened. In past missions, we did not have sensors, and the sensors were not that good, and they were not appropriately placed for us to maximize the information that we get. But this time around, it was different. We really extensively instrumented it with instruments that are developed here called the Medley sensor. And it really shows us this is the real data you're looking at from Mars during entry. And you can see that the in-depth heat shield temperature reached close to 2,000 Fahrenheit, which is in-depth. At the surface, we estimate the temperature to be around 2,900 Fahrenheit, which is hot enough to melt iron. And the Pico heat shield, we also measured how much of the material got removed. And as you may imagine, these are ablative heat shields, and they sacrifice themselves as they go through the entry process. And we found that through our instruments that we had embedded, we found that it lost less than 1/10 of an inch of material, where we were expecting it to lose about 2/10 of an inch, and we were prepared. We designed the heat shield for it to lose about 1/2 inch of material. So it did better than what we thought. This is an image of the heat shields being separated. This is an actual photograph taken from onboard during entry, descent, and landing. You can see Mars surface in the background, and heat shields separated from the bottom of the vehicle and falling away. And finally, a perfect landing. Because of all the technologies that came together and worked so well, we were able to land about 1.5 miles from the target site in Gale Crater. This is the Mount Sharp. This is the predicted landing ellipse where we would have landed, and this is where the target site is. We landed about 1.5 miles away. This ellipse is about 12 kilometers wide. Sorry about the units. So after traveling 340 miles for about 8-9 months, MSL delivered a 900 kilogram Curiosity rover within 1.5 miles from the target site. This is the kind of precision we need for human missions so that we can deposit assets on the surface of Mars before the humans arrive there. So my final slide, well, of course, this has been an exciting year. I remember that day and that time when some of us were at JPL, crossing our fingers, watching how this thing is going. In the last year, we've learned more about Mars entry because of the way it performed, the way we had instrumented them. We learned more about that in the last 1 year than we had in the past 40 years. And the Ames developed Pico thermal protection system performed better than expected. And with the knowledge that we gained from this mission, we're learning to develop more capable entry vehicles and technologies that need to be developed for us to take, for humans to go to Mars one day. So thank you very, very much.